Okay, so problem 2.1 out of Griffith's Quantum Mechanics textbook. And before I start this, if you wouldn't mind please liking and subscribing, I'd greatly appreciate it. And I'll be posting more solutions to this textbook solution as well as other common undergrad physics textbook solutions. Okay, so 2.1 is proving these different theorems, and the first one wants us to prove that for normalizable solutions, the separation constant E must be real. It gives us a hint with two equations, which I've written down here. And it tells us to write E as a complex number. Okay. So the way that we're going to do this is we're going to essentially plug all this in. So psi of xt is, of course, our time independent psi of x times our time dependence. So minus I times. So our E is now a complex term, and we're going to express it as such. All over h bar. And now we can plug that into equation 1.20. Okay? So what we're going to do there is we're going to integrate from negative infinity to positive infinity. And it will be psi x e to the minus I. So we're just going to write down our whole thing here. Times, and I'm going to shorthand this, square this, and then multiply it by the complex conjugate. That becomes positive I e minus I t over h bar. Okay. All right. So, and this is of course dx, and our normalization constant basically tells us that this needs to equal a probability of 1. Okay, so these terms have no x dependence, so I can go ahead and put that out here. And I'm just going to distribute everything. So minus I et. So we're going to have a minus I squared. I squared is -1, so that'll be plus r gamma t over h bar times, and then, oops, let me fix that text mode there. Same thing here. Text mode is kind of annoying on this app. I think I complain about it every video. Okay, and then of course, just as before, we're going to have plus, and then of course our integral. Okay. All right, well, we can add our exponents here because they have the same base e. And when we do that, we're going to get, this term here. Obviously, if you subtract those are going to go away. And these two terms here will add. Okay, so that's just going to be 2 gamma t over h bar. I'll write that a little higher. I hate when my exponents are down towards the base. 2 gamma t over h bar. Our integral over all space, psi x dx. Okay? Now, we want this to be normalizable, a normalizable solution. Okay? And in order for this to be the case, what that means is this has to be a constant. Okay? Well, the only constant that we really want to look at here is the gamma. 2 and 8's bar, those obviously have their own values. And gamma is what we're proving needs to be 0, because that was part of that was on the imaginary part here. That was our imaginary number. Okay? And t is obviously time, that's going to vary. So tau equaling 0, then e to the 0 is just 1. And we get our normalization condition. So that was part A. Part A. Part B says that the time-independent wave function can always be taken to be real. It doesn't mean that every solution is real, but if you have one that's not, you can express it as a linear combination of solutions that are real. So you might as well stick with sides that are real. It gives us a little hint here, and it says 2.5, which I think is just, let's see here. Let me just confirm what 2.5 is. Yeah, it's just Schrodinger's equation. Okay, cool, good deal. And it gives us a little hint here that real linear combination of psi plus psi star and I times psi minus psi star are 2 real examples. So let's start with, I'm not super sure like what every professor wants you to, if they want to show like that the linear combination is, or that this specific one is, but I'm just going to kind of work it a lot here. So we have Schrodinger's equation. Okay, so we have Schrodinger's equation, and we know psi is obviously a solution to Schrodinger's equation. Now, the examples they give us, we also want to show that psi star is a solution. Well, that's kind of simple if you just take the complex conjugate. It's supposed to be a partial. Clearly, nothing has changed except our wave function is now the complex conjugate of psi, which is still a solution to the Schrodinger equation. So if psi is a solution, so is psi star. Now, what we want to show is that a linear combination is also a solution. So if you have, let's call it psi 1, yeah, that's fine. Psi 1 is equal to psi 2 plus psi 3. And these independently are solutions to the Schrodinger equation. Then we want to show that psi 1 is also 1. So again, we're going to use Schrodinger's equation just to show that that is a solution. And then from there, we'll be able to put together what they want. So Schrodinger's equation, and now we're going to, everywhere we have psi 1, we're going to expand it as psi 2 plus psi 3, a linear combination. So what I'm going to do here is, instead of putting psi 1, we'll do the second derivative of psi 2 with respect to x. Another thing we actually want to show, so linear combination can also include, so let's write this. Oops. I'm going to add a constant here, so we'll say C1. Probably should have named this better, but I guess it's fine. So these are just constants, C1, C2. So a linear combination can be multiplied by some sort of constant. So I'm just going to also include that as well. Okay. So we have minus h bar squared over 2m c1, the second derivative of psi 1 with respect to x, minus h bar squared over 2m c2, and then the second derivative of psi 3 with respect to x, plus our potential times psi, so c1 psi 2 plus v c2 psi 3. Okay. And we're just going to express this. We're going to factor out these constants. So we have c1 times minus h bar squared over 2m, the second derivative of psi 2 with respect to x, plus the potential psi 2, plus c2 times minus h bar squared over 2m, second derivative of psi with respect to x, psi 3 that is, plus v psi 3. Okay. And what is this? Well, this is just e psi 2, and this is e psi 3, because that's what Schrodinger's equation is. So you get c1 e c1 psi 2 plus e c2 psi, I'm sorry, this is psi 2 psi 3. There we go. And let's do this. Psi 3. So once again, we have a solutions to Schrodinger equation where it's a linear combination. And why is that important? Well, then it's pretty easy to see that psi plus psi star is a solution. Why? Well, psi is a solution, and so is psi star, and the linear combination of them is also a solution. And same thing here. I psi minus psi star is also a solution. And the benefit of this is if you were to write psi as a complex number, let's say a plus bi, and you take the complex conjugate of that, of course, if you plug these in, so let's say this is equation 1, this is equation 2, if you plug it into equation 1, a plus bi plus a minus bi is 2a. So you can see equation 1 is real. And as for the second equation, you have a plus bi minus a plus bi. So you have I times 2bi, which is just 2bi squared, which we know to be -1. Okay? So those are, in fact, solutions. They're real. And again, I'm not sure how much your professor wants you to kind of assume, but I just wanted to show that if psi is a solution, psi star is a solution, and if you have psi 2 and 3 is a solution, a linear combination of those two is also a solution, and then the rest kind of falls into place. So part C, the last part of this, says, now this says if v of x is an even function, then psi of x can always be taken to be either even or odd. So let's go do that. So let's start by writing down Schrodinger's equation. So minus h bar squared over 2m, the second derivative of psi with respect to x, plus v of minus x, psi of minus x, so we're replacing our x with minus x, equals e psi minus x. And here, we're saying that v of minus x is equal to v of x. V of x is even, so by definition, that's what it means. So just putting that in really quick. what we can see is that psi of minus x is also a solution to Schrodinger's equation. Okay? So psi of minus x is also a solution. And in terms of the linear combination of even and odds, well, let's call psi e for even. Make that a little smaller. E of x as psi of x plus psi of minus x. And I call that even because it is even. If you were to replace x with minus x, right, it is just what we're calling psi e of x. Okay? And by that same logic, we can define an odd function. Except instead of a plus, we're going to call it minus psi of minus x. And then, if we substitute x with minus x, which is just, minus psi odd x. Okay? And the reason why we know that these are solutions, the even and odd, is because they're a linear combination of two solutions that we do know, psi of x and psi of minus x. Well, if psi e and psi o are both solutions, then a linear combination of them is also a solution. So you can write a solution as a linear combination of these even and odd functions. Hopefully that makes sense, and if it did, please like the video and subscribe. Thank you.